With AI gaining traction over the past few years, understanding how neural networks work at a fundamental level has never been more important. However, with libraries like PyTorch and TensorFlow abstracting away most of the complexity surrounding neural networks, this understanding is lost. In this series, I'm going to try and change that by explaining what a neural network is, the math involved, and building one from scratch in Python using only the NumPy library. The first video in the series will dive into the math. Strictly speaking, although the math is not required to code a neural network, understanding it is beneficial to find further optimizations and improve the neural network library we write. We will discuss the forward pass in neural networks, the role of activation functions, the chain rule from calculus to understand the basics of backpropagation, and introduce linear algebra to optimize the computations in this video. The second video will involve setting up the classes in our neural network library and coding the forward pass of the neural network. We will also write some activation and loss functions in this video. In the third video, we will implement backpropagation for the stochastic gradient descent case and generalize it to work for any batch size. Finally, we will use our neural network library to build a handwritten digits classifier. At the end, I will upload a video with all the parts for those who would like to watch it and work on the project in one sitting. The code will also be available on my GitHub, linked in the description down below. Look forward to seeing you all in the first video of the series. Welcome to the first video in this neural network series. Today, we will learn the math behind neural networks. However, before we jump into that, we need to review a couple of concepts. First, matrix multiplication. Matrices and their higher dimensional analog, tensors, are a common way to represent data in arrays. This is often the case with the weights and biases in a neural network. And using matrix multiplication, we can have the model make predictions. So, if we want to multiply two matrices together, we must ensure that their shapes match. That is, the number of columns of the first matrix must be equal to the number of rows of the second matrix. The resulting matrix will also have as many rows as the first matrix and columns as the second matrix. Now, to see why, let us take this example and manually multiply these two matrices. We first have to multiply the first column of the second matrix with each row of the first matrix and use the results to fill out the first column of the resulting matrix. We then repeat this with the remaining columns of the second matrix to get the result of multiplying the two matrices. The second concept we need to go over is the chain rule. Now, differentiation is the process of finding the derivative of a function. And physically, the derivative can be understood as the slope of a function, and it tells us how fast the function is changing with respect to an independent variable. For example, here, the function is changing quickly at this point and has a large derivative and slope, while here it is changing slowly and has a small derivative. Derivatives of a function are always calculated with respect to an independent variable. However, when we have functions which vary with respect to other functions of the independent variable, we must use the chain rule to find its derivative. For example, here f is a function of g, which is in turn a function of x. So to find its derivative, we need to find how f varies with respect to g and how the function g varies with respect to x. Now that we've gotten the basics down, let's move on to discussing neural networks. A canonical neural network you may have seen before would look like this, with neurons and connections between them. Here, the first layer where the data is input to the model is called the input layer, and the last layer where the model generates its outputs is called the output layer. All intermediate layers are called hidden layers. The model works by taking inputs to each layer, multiplying them by their corresponding weights, represented by these colored arrows, adding an optional bias term, and passing the result or pre-activated output onto the next layer. To understand this math, let's simplify this down to a one neuron input and output model. Given an input x in this model, the output, if the weight of this edge was w and there was a bias term b, would be wx plus b. Now, this looks like the equation of a line. In fact, if this model is allowed to train and optimize the loss function, that is, minimize the error between its predictions and the expected output, we would arrive at a linear regression solution. But unfortunately, Most relationships in real life are hardly linear, and we need to introduce some non-linearities into our model. We do this by using activation functions. These functions take these pre-activated outputs of each layer, pass them through a nonlinear function, and return the activated output. Some common functions that are used for these are ReLU, Sigmoid, Tanh, and Softmax. This process of multiplying the layer inputs with the weights, adding a bias term, and applying an activation function to get the layer output is repeated in every layer of the neural network to get the model's output to a given set of inputs. This process is called the forward pass of the neural network. The model prediction at the end is then compared to the expected output, and the error is calculated using a loss function. Now, there are different kinds of loss functions for different purposes. Two of the most common types of tasks neural networks are used for are regression and classification. Regression involves finding a function that maps the input parameters to the output parameters. For example, linear regression, where we try to fit a line to a set of data. In these tasks, the mean squared error is a commonly used loss function. The other task, classification, involves classifying an object with certain input parameters into two or more classes. For these tasks, the two most common loss functions are the binary cross-entropy loss and the categorical cross-entropy loss. Now, so far we have explored the predictive capabilities of a neural network. That is, given an input, what would the model predict to be the output? However, what if the prediction is wrong? And this often happens when the model is not yet trained, when the model has random weights and biases instantiated. That is when the error that is calculated by the loss function must be propagated through the model, and the weights and biases need to be adjusted to improve the prediction. And this is where backpropagation comes in. The core idea behind backpropagation is gradient descent to minimize the loss function. This is an iterative algorithm that attempts to find the combination of weights and biases that minimizes the model's error on the training data. That's a lot of words. Let's just go back to a simple one input, one output example and work through it. The only parameter in this model is the weight W. Suppose the prediction of the model is very close to the expected output. Then the update to the weight is small to improve the model accuracy. Conversely, if the prediction is far off, the update needs to be more drastic. We can make these conclusions because the output depends solely on W. If there are more weights and biases in the network, then the updates to each weight are determined by the effect that that weight has on the model output. To calculate this quantity, we need to find the derivative of the model output with respect to that particular weight. And this is where the chain rule comes in. Let's use the chain rule in the one input, one output case from before. We'll include an activation function f in this example as well. Assuming that the pre-activated output is z, the model output is O, the expected value is E, and the loss function we are using is the mean squared error, the loss will be O minus E squared. We want to find the derivative of the loss function with respect to the weight W. Using the chain rule, we can calculate this as del loss over del O times del O over del Z times del Z over del W. Because the loss function depends on the model output, which in turn depends on the pre-activated output because of the activation function, and the pre-activated output depends on the weight W. To fully understand backpropagation, let's consider this extended case. Note that the lowercase letters in the hidden layer represent the pre-activated output, while the uppercase letters represent the activated output. The effect each weight has can be calculated as follows. We simply look at each path from the output node to each inner node and find the derivatives up to that point. If we observe these terms carefully now, we notice that the first three terms in the product were kind of calculated in the last layer of the neural network. The only difference is that these terms are derivatives with respect to A and B, not W3 or W4. This is crucial because this means that we can reuse computations of these red terms from previous layers while calculating derivatives. In fact, this is where the name backpropagation comes from. The gradients calculated in one layer are propagated backwards to previous layers, drastically reducing the number of computations required. Another important fact to notice here is that the effects of each weight And the updated derivatives to propagate to the previous layer can also be calculated using matrices as follows. This is how we will implement the backward pass in the code. After this backward pass is complete through all the layers of the model, the weights are updated by subtracting the update matrix. Oftentimes, the update matrix is also scaled by a value called alpha or learning rate to ensure that the optimization algorithm does not jump over the minimum. One final thing we need to keep in mind is that training the model on one example at a time is called stochastic gradient descent, and it can be ineffective in some cases because of extreme or outlier data points. So, the common remedy is to train in batches. Each batch contains multiple input data points that are processed together. For example, a common batch size is 32, which means that the neural network makes predictions for 32 examples at a time and uses the aggregated error from all 32 examples to update its weights. This reduces the chance that a few outliers drastically alter the program weights, and since we're using matrix multiplication, can be a little bit more efficient. We will implement the neural network with a batch size parameter, which should clarify this concept. And that's all the math involved in neural networks. If any parts are unclear to you, be sure to rewatch them either now or after walking through the implementation with me. Thanks for watching, and I'll see you in the next one, where we begin implementing the neural network library. In this video, we will begin implementing our neural network library. At first, we will go through the design of the library. Then we'll implement the layer and layer list classes. We'll implement a few activation functions that we discussed last video, and we'll round it off by implementing the forward pass through the neural network. I would strongly recommend you try and implement the classes and functions we discuss before you watch me do them in the video, as this will help solidify the theory we discussed in the previous video. All the code will be posted on my GitHub, which will be linked in the description down below. Now, without further ado, let's get into the design of our library. We're first going to write two classes, layer and layer list. The layer class will represent a single layer in our neural network module. The layer list class will represent the entire neural network model. After we're done initializing the classes, we're going to write three activation functions, which we discussed in the previous video. We're going to cover ReLU, Sigmoid, and Softmax. Now, this Wikipedia link has a lot more activation functions that you should go and explore and try implementing by yourself. After that, we're going to tie everything together and implement the forward pass of a neural network. Let's get started with initializing the layer class. I'm going to write the constructor method, and we're going to take in a couple of parameters. So we're first going to take in the input size. So this will be the number of neurons that are the inputs to the current layer. The output size, which will be the number of output neurons in the layer. An alpha value to specify the learning rate of the model. An optional bias term, which we'll set to false by default. A batch size term, because we want to train the model in batches. And finally, an activation function, which we'll set to be none by default. We'll start off by initializing attributes in the layer class to store each of these values. So self.input size is equal to input size, and so on. Now, let's also store the weights and biases of the current layer in a NumPy array. This will be self.weights is equal to np.random.rand and self.input size, self.output size. This is going to create a NumPy array instantiated with random values of shape input size by output size, and this will represent the weights. Now, if there is a bias term, looks like I forgot to include an attribute to store the bias term, so we'll add that in. And next, if there is a bias term, we're going to include another row in the weights matrix to store the bias values. So we'll do that as follows: self.weights equal to np.vstack. This essentially stacks two matrices vertically. So we're going to update our weights parameter and add on a row of random values representing the bias terms. np.random.rand 1, self.output size. And that's the entire constructor for our layer class. Let's now write the constructor for the layer list class once again. And we're going to take in a list of layers in the initializer list for the layer list class. And we're going to store the model as a list of these layers. We're also going to add an append method so that if we want, we can add additional layer objects to our model after the initialization. So this would again look like this. And for layer in layers, self.model.append layer. Now let's also write a couple of getter and setter methods for these classes, which will become useful later on when we're implementing other parts of our library. We'll first write a getter method in the layer class called getBatchSize. This function will return the batch size of the current layer. And we'll also write a def set alpha method, which will set the alpha value in the current layer to be this new alpha value. Let's say new alpha. The reason we're doing this is that when we're training, if we're getting close to our optimal minimum solution during the gradient descent algorithm, we might want to reduce the alpha value so as not to overshoot the minimum. And similarly, we'll need to write a set alpha value in the layer list class because the layer list class is going to control the alpha value of every single layer in the module. So we're going to write set alpha. We're going to take a new alpha value and we're going to iterate through all the layers in the self.model list. So that would look as follows: for layer in self.model. And for each layer, we're going to call its set alpha method as follows and pass in the new alpha value. So that's the basic structure of our layer and layer list classes. We still have to implement the forward pass, but we will do that after we're done implementing a couple of these activation functions. Now, as we discussed in the previous video, if we did not have activation functions in a neural network, then all that the neural network would be able to recognize is a linear function. Now, activation functions work by taking in the matrix product of the inputs and the weights of a layer and passing them into a nonlinear function, for example, ReLU, Sigmoid, and Softmax, and returning the output of that function as the layer output. So let's take the example of ReLU. ReLU is defined as, let me put it in as a doc string. ReLU is defined as a function, so we can write it as f of x is equal to a piecewise function which will return 0 when x is less than or equal to 0, and it will return x when x is greater than 0. Let's put some more spacing here. So this is what the piecewise function ReLU does. And as you can see, it's nonlinear in that there isn't a single line that describes this function. There are in fact two lines. When x is less than 0, that is on the left half of the coordinate plane, the value output by ReLU will just be 0, and on the right half, the value will just be equal to x, which would be the same as the line y equal to x. Now, the reason we'd want this is if we have a layer where we only care about outputs, if the output is positive, then we would use ReLU to cancel out all negative outputs of a layer. So to implement ReLU, we're going to define this dunder method, def call, and we're going to pass into it the pre-activated output of a layer. And what we want is that for each value in the pre-activated output, we run this function f of x and return the results. So since this is essentially an if-else condition, we can use the np.where function defined in the NumPy library, which handles that condition and returns the corresponding value. So we're going to say where pre-activated output is less than 0, or less than and equal to 0, we're going to return 0, and otherwise we're going to return 1, and we're going to multiply this with the pre-activated output. And this is the NumPy array that we're going to return. Essentially what this does is if the pre-activated output is less than 0, then we're going to multiply it with 0, essentially canceling it out. Otherwise, we're going to multiply it with 1 or retain its value. Now, the sigmoid function is similar. The sigmoid function works as follows. It takes an input x and it returns to you the value 1 divided by 1 plus e to the negative x. The implementation is very straightforward. We once again write our call dunder method. We pass in the pre-activated output. And we return this exact formula. So 1 divided by np.exp, which is essentially going to take the exponent of pre-activated output. That's the sigmoid function. Similarly, we're going to define the softmax function. And we're again going to take the pre-activated output. And one thing we have to keep in mind is that the softmax function is unlike our previous two activation functions, which acted on each value in the activated output matrix. Softmax, on the other hand, acts on all the values in the pre-activated output. Let's say that the pre-activated output is equal to 1, 2, 3. Or let's just make this negative 3. Now, if I pass this to ReLU, then the output I would get would be 1, 2, 0. Because 1 is greater than 0, 2 is greater than 0, while negative 3 is less than 0. So only negative 3 gets cancelled out and the others retain their value. On the other hand, if I pass this into softmax, he's going to do a couple of things. He's first going to create a matrix where he raises e to the power of each value in the pre-activated output. So it will become e squared, and e to the negative 3. After that, he will calculate a denominator, and that would be the sum of all values in this matrix. So that would look as e plus e squared plus e to the negative 3. After this, let's just try this as exponents. And after this, what he's going to do is he's going to return xnum divided by denominator. So essentially, the first term would look like e divided by this denominator. The second term would look like e squared divided by this denominator. And the third term would look like e to the negative 3 divided by the denominator. Now, the reason for this is that the softmax function is usually used to convert a list of layer outputs into possible probabilities. And this is often used as the last layer's activation function in a classification task. So we're going to implement this slightly differently. What we're going to do is we're going to define a variable called x shifted. And we're going to say this is np.exp, which is essentially e to the power. And we're going to say pre-activated output minus np.max pre-activated output. And we also want to do this on the axis equal to 1 and keep the dimensions equal to true. So what this axis parameter is saying is it's telling the function to act on the first axis, which is all the rows of the pre-activated output, and keep dimensions is ensuring that the value or the matrix returned by np.max is of the same shape as pre-activated output, which would allow them to be subtracted. So if we break this down, what this line of code is doing is simply finding the maximum value in the pre-activated output, which in this case would be 2. Next, it's going to subtract that value from each value in the pre-activated output matrix. So the matrix will become -1, 0, and -5. And then it's calculating x shifted as this matrix, e to the -1, e to the 0, and e to the -5. Now, if we finish off the function, we can see exactly why it's doing this. We also will store a value called denominator, and this will simply be the sum of x shifted. So that's just summing all of these values, and we're going to return x shifted divided by denominator. Now, this is equivalent to finding the value of softmax as explained here, and it's a little bit of exponents and manipulating exponents, but then you can easily prove this to yourself. But this is equivalent. And the reason we're doing this is, let's say that the value in the pre-activated output matrix was a large number, let's say 2000, and then we had 0. What would happen then is that this value 2000, if we take e to the power of 2000, we would get a very large value. In fact, the value is so large that Python would classify it to be infinity. And if we get infinity in our calculations, then it's likely to propagate through the model, and we're going to get incomprehensible results. Because obviously you can't multiply anything with infinity or add anything to infinity, so that would just throw the entire model off. By shifting the exponent, that is by subtracting every value with this max value, we would get 0 and -2000. E to the 0 is simply 1, and it's not a very large value, and it can be handled by a model. And if we have e to the -2000, well, that's a very small value, and Python will approximate that to be 0. And since Softmax is essentially trying to assign probabilities to the values, we obviously expect the pre-activated output with value 2000 to have a much greater probability than the value 0, and this would make sense because 2000 would be given a probability of 1 and e to the -2000 would be given a probability of 0. This issue, where raising e to a big number could lead to an infinite value being generated, would also appear in the sigmoid function. So one more thing we have to do here is assign pre-activated output to be equal to np.clip pre-activated output -1000, 1000. So what this is doing is it's going through each value in the pre-activated output matrix, and if there's any number smaller than -1000, it'll just get assigned the value -1000, and any number greater than 1000 will get assigned the value 1000. And those are all the activation functions that we will write in this video. I would suggest you try and implement a few more activation functions from the Wikipedia page. A couple I would recommend would be the binary step function and the tanh function. Now, returning to our layer and layer list classes, we can now implement the forward pass of the neural network. We'll implement it similarly using a called under method. And we're going to take the layer inputs as the arguments to this class. Then what we need to do is a very simple matrix multiplication. As we discussed in the previous video, we simply need to multiply the layer inputs with the self.weights, and this will give us the expected output for the layer, and that would just be it. for the forward pass. The only thing is that we have a couple of edge cases to handle. The first one is if there is a bias term, in order to ensure that the two matrices match. So let me just write down the shapes of the matrices that we expect. We expect layer inputs to be of shape batch size by self.inputs. Or let's just say input size. Input size. And we expect our self.weights to be input size by output size. Now these shapes obviously match because we're multiplying these two matrices, and the number of rows in the second matrix is equal to the number of columns in the first. Now, if there is a bias term, however, the self.weights matrix will have another row in the matrix. And to account for that, we need to add a column of ones to the layer inputs. So if there is a bias term, then our layer inputs would become equal to np.hstack. So this is going to stack two NumPy arrays horizontally, and that's what we want to do when we want to add a column of ones. So this is going to be layer inputs here, and np.ones shape would be self.batch size, which is what we stored here in the initialization function, comma 1. Now we can do this matrix multiplication. And finally, if the layer does have an activation function, remember we initialized it to not have any activation function by default. Now, if it's not none, that is there is an activation function, then we have to call that activation function on the layer output. And this will be our new layer output. And that's what we will return from this layer. So what this called under method is doing is it's going to first change the shape of layer inputs by adding a column of ones if necessary, that is if there's a bias term. Then it will use matrix multiplication to calculate the pre-activated output. After that, it'll pass it into an activation function if there is one for the layer. And finally, it will return the layer output to the calling function. Now the calling function will be implemented in this layer list class. We're going to define another call here. The call method will take an input. We'll call it model input. We'll assign it to intermediate results. And then for each layer in self.model, we will pass in the intermediate results matrix, and we'll assign the result from the layer back to intermediate results. Essentially what this is doing is it's taking the input to the model, passing it into the first layer, getting the result, and passing that result onto the next layer, and so on. So this is essentially completing the forward pass through the layer. And at the end, we're going to return intermediate results as the final result of the model prediction. And that's it. That's the entire forward pass through a neural network. Let's quickly test it out. I'm going to write the if name double equal to main if statement to test this bit of code within the layer file. We're going to define our model to be a layer list. So this is going to be a model, and we're going to have just two layers in there. Let's have one input and one output in the first layer. We'll not add any bias terms. And in the second layer, we will take one input and get two outputs. And then for activation function, let's give it softmax. Now, in order to use the softmax function, which is defined in the activations.py file, we're going to just import all the activation functions using the syntax from activations, import star. This is going to import all the activation functions we define in this file. With this model, let's just give one input. So np.array, let's give it one input of just one, and we'll call this int. And now, if we use this syntax, model imp, we're going to pass this input matrix into the model, into this call function, and we're going to get the results after it passes through both of these layers as the output, which we can print. To see that this is working, let's just add a couple of print statements. Here, we're going to print self.weights to view the weights in the current layer, as well as print the layer output here because we want to view Softmax in action. And with that, let's just run the code. Oh, oops. Looks like I forgot a couple of things. So the alpha and batch size values here are not set to any values by default. So we need to pass that in when we define the layers here. We'll just set alpha to be 0.1 because we don't really use it yet. We're going to use that when we do the backpropagation in the next video. And we'll set the batch size to just be equal to 1. Same thing here. Let's just fix the spacing and let's run this. Tuple object cannot be interpreted as an integer. Oh, okay. So this just takes the shape as a list of variables. It doesn't have to be passed in as a tuple. Similarly here, we just pass it in as separate arguments and not as a tuple. And yep, let me just clear it and run it again. So the first values that we see here, the weights of each layer, the first layer has a weight equal to this, and the second layer has 2 weights with these values. Next, when we ask the model to predict the output for an input of 1, that's going to be passed through the first layer, where 1 is going to be multiplied with this weight. So the output is going to be 0.9386, the same as the weight. And next, when it's passed through the second layer, the first output would be this value multiplied by 0.2, which should give us 0.19. And the second value will be 0.93 multiplied by 0.69, which will give us 0.647. Next, if we convert these into probabilities using the softmax function, we should get these values. So if we wanted to calculate that by hand, the first value should be e to the power of 0.19. The second value should be e to the power of 0.647. And let's just store their sum here. And the values will be this divided by the sum. I'm going to just say s is this divided by s. And this will be this divided by s. Let's just quickly check this in the Python interpreter. So we'll say s is equal to, or we should say from math import exp. I'm importing the exponential function from the math library. I'm going to store s as equal to exp 0.19 plus exp 0.647, and we'll say print exp 0.19 divided by s, which is 0.38769, which is close enough to what we got here. And if we print the other value, exp 0.647 divided by s, we get 0.6122, which is the same as what we got here. So that shows that the activation functions we wrote work, and so does the forward pass through our neural network. Now, we could, of course, test the other activation functions and the bias terms and whatnot, but I'll leave that up as an exercise to you guys. I'll see you all in the next video where we implement backpropagation in our neural network library. In this video, we will complete the implementation of our neural network library. The main algorithm that we need to implement is backpropagation. Without further ado, let's get straight in. In the math video, we discussed how, at the end of the model forward pass, we have a loss function to calculate how wrong the model's predictions are compared to the expected output. We're going to first implement these loss functions. To kickstart backpropagation, we need to find the derivative of this error with respect to the model's predictions. You might also remember me mentioning that in the implementation, we will directly calculate the gradients to reduce the computations. Here, we're going to implement these three loss functions: the mean squared error, the log loss function, and the categorical cross entropy loss function. For our convenience, I have already implemented these before because they are just simple formulas and deriving them would require a separate video by itself. So if we quickly go through these functions, the mean squared error, which is what we would normally use for regression tasks, takes the predicted and the expected NumPy arrays, finds the shape of the predicted output, which would be the number of examples, and then it would find the difference between the predicted and expected values, multiplied by 2 and divided by n. What this is doing is averaging out the individual errors between the predictions. The log loss and categorical cross entropy loss functions, on the other hand, are meant for classification tasks. The log loss function is often used when we have a classification task with two output labels. And the categorical cross entropy loss is used for classification tasks with more than two labels. Here too, you can observe that we're using the clip function to clip the output values to be slightly greater than 0 and slightly less than 1. And the reason being that here we're dividing the expected values by the predicted values, and if any value that is predicted is equal to 0, then we would get a division by 0 error. So those are the loss functions that we'll be using in our neural network library. Now let's move on to the activation functions. In the previous video, we implemented these call methods for ReLU, Sigmoid, and Softmax activation functions. Now we're going to implement this derivative method. What the derivative method is going to do is it will take the gradients calculated up to the next layer and calculate the gradients with respect to the activation function for the current layer. Since the activation function changes the pre-activated output of the layer into an activated output, we need to find the rate at which this change is affecting the error, and that is why we need these derivative methods. Now, if you recall from the previous video, whenever the ReLU input is less than 0, the output will be equal to 0, and if it's greater than 0, it will be equal to the output itself. We also discussed that this means that ReLU is a combination of a horizontal line and the line y equal to x. So if we find the derivative, we're going to have to return these values. So we're going to use the np.where function, and we're going to check where the output is less than 0, less than equal to 0, and return 0, and otherwise we're going to return 1. We're going to multiply this with the gradient so far. What this is doing is it's checking if the output, maybe we should rename this to be pre-activated output. So if the pre-activated output is less than or equal to 0, then ReLU would output 0 as its activated value. So the gradient at that point would be equal to 0. Similarly, if the pre-activated output is greater than 0, then the output would just be the pre-activated output, which would lie on the line y equal to x. The slope of the line y equal to x is simply 1, which is why we're going to return 1 here as the derivative. And if we remember from backpropagation, that is simply multiplying the gradients that we've calculated so far, that is reusing those gradient values and multiplying it with the current derivative because of the chain rule. So this is how we would implement the derivative method for the ReLU class. Moving on to Sigmoid, I'm going to make the same change here. I'm going to update output to be pre-activated output. And even here for Softmax, we'll change output to be pre-activated output. Now, for Sigmoid, let's not get too deep into the math, but the derivative is simply going to be this value that we've calculated here times 1 minus the same value. Now, if you've taken a calculus class before, then you would be able to derive the derivative of 1 over 1 plus e to the negative x, and you would recognize that you would get this expression here. And let's not forget, we need to multiply that result by the gradients calculated so far. Finally, we have to implement the softmax derivative method. Now, since softmax acts on each row in the pre-activated output matrix and not just each value in the matrix, we have to do some more math here. I'm not going to go too deep into this because it involves vector calculus. So let's just say that this is how we find the derivative of the softmax function. We first run the pre-activated output through the softmax layer once again in order to calculate the activated output. Then we get the batch size and the number of classes, which are the rows and columns of the output matrix. Then we have to calculate this Jacobian matrix. And then for each example in the batch size, we have to create a couple of more matrices. And then we can do some linear algebra to find the derivatives up to the softmax layer. Now that we've implemented the gradient calculations for the output of the model and for each activation function, we can implement backpropagation for a single layer. We're going to do that in this back method in the layer class. So once again, the back method just works in reverse of the call method. So we're first going to check if there is any activation function. If there is an activation function, we're simply going to call the activation function's derivative method that we defined just now in the activations file. The derivative method expects the pre-activated output and the gradients calculated so far, which would be in the ret variable. And this would be our new gradients calculation. Then we have to find the update matrix, which would just be the current inputs matrix multiplied with the ret variable. Then we have to find the return value from this function, which would be this variable new ret, and this will simply be ret matrix multiplied with self.weights. Now finally, we have to account for the bias in the layer. If there is a bias term, new ret will be equal to all the rows and all but the last column, because the last column contains all the bias terms. Then we return the new ret value to be propagated backwards to the previous layer. Now, if you notice here, we need to use the current inputs to the layer, the pre-activated output, and we need a variable called the update matrix. So we're going to initialize these values to be none in the constructor of the layer class. So self.update matrix is equal to none, self.current inputs equal to none, and self.pre-activated output equal to none. Next, when we're doing the forward pass through the layer, we're going to store the current inputs to the layer in the current inputs attribute by copying it. The reason we need to copy the layer inputs is because if we simply set them to be equal, this is going to equate the references. That is, any modifications to layer inputs would also modify current inputs, but we do not want that to happen. So we have to copy the value over to the current inputs attribute. Next, if there's also the activation function, then we'll copy over the pre-activated outputs. Layer output. This way, we can use these variables in the back method of the layer class. And this would have to be self.preactivated output. Finally, after backpropagation is completed in all the layers of the model, we'll have to update the weights, and we do that as follows. Self.weights minus equals self.alpha times self.update matrix. This is, as you recall from the math video, how we update the weights. We scale the update matrix by the learning rate to ensure that we don't miss the minimum during the optimization process. And we also reset all of these values that we initialized here back to none for the next pass through the neural network. That, in a sense, is backpropagation through a single layer of the model. Now we have to implement backpropagation for the entire model. We're going to do that in the layer list class by writing its own back and its own step methods. What the back method will do is for each layer in self.model in reverse, this syntax ensures that we're iterating through the model in reverse, which is how we would do backpropagation. We're going to call the back method and pass in the gradients calculated so far, which will be this error variable. And then we'll store the return value back in the error variable to be propagated on to the previous layer. And finally, to update the weights in every single layer, we're going to iterate through all the layers once again in the model and call the layer.update function. This will update the weights and biases in all the layers of the model. And with that, we have implemented the forward pass through the neural network and the backward pass. We're just going to add a couple more methods to the layer list class, which would allow the user to train the model without having to combine all these functions by themselves. First, we're going to write this method called fit. What fit does is it will implement the training loop of the model. It's going to take a bunch of training data, the expected values. It will pass the training data through the model epochs number of times, and epochs just means how many times the input data will be seen by the model, and we're going to train the model. We'll take a couple more parameters, alpha and batch size. Alpha will be the initial alpha value, the initial learning rate of the model, and batch size will indicate the size of the batches we wish to use during our training. We'll also take this parameter, loss deriv function, which is going to be one of these loss functions that we defined in the loss file. That will allow us to calculate the derivatives to kickstart the backpropagation. We're going to start off by writing an outer loop to iterate as many times as epochs. So the contents of this loop will run as many times as epochs. And in each epoch, we need to feed the entire input data into the model. First, we're going to create batches of the input data by calling this batch static method that we've defined up here. That would look as follows. We'd get batched input, batched expected is equal to layer list dot batch input data expected batch size. Next, for I in range len batched input, that is for each input batch in our batched input variable, we're going to pass this in to our model and we're going to get the predictions. This will be model output is equal to self batched input. This is going to pass the batched input into the model and return the model output by calling the call method. Then we're going to call self.back to backpropagate the error. The initial error will be calculated by calling the loss deriv function. And to that, we have to pass the model output or the model's predictions and the expected values, which we can do as follows. After we've calculated the derivatives in all the layers of the model, we have to call the step method to update the weights and biases in the model. Now, before we start the training loop, we want to call the alpha update, which was the set alpha method, to set the initial learning rate in all the layers of our model as follows. And we're going to periodically update this alpha value. So I'm going to say prev update is equal to 1. And here, instead of just having an underscore, let's say for e in range epochs, we're going to run through this training loop. And if e is 10 times the previous update, then we're going to set the alpha value to be a new alpha value. And we'll calculate this new alpha value by dividing the previous value by 10. We should also update the previous update variable to be this new point. That, in a sense, is our training loop. Now we have to implement this batch static method, which we're going to do as follows. We're going to get num data is equal to input data dot shape. This way we're going to get the number of examples in the input data. Next, we're going to store the indices of all of these data points as follows. I in range num data. Then we're going to shuffle these indices because we want to pass the data points into the model in a random order. To randomize the values in the indices list, we're going to call the shuffle function. The shuffle function is defined in the random library, which we'll import as follows. After we've shuffled all the indices, we're going to create two lists, batched inputs, batched expected, and we're going to return these values at the end of the function. These two lists are going to contain the batched input data and the batched expected values. Let's also just convert these into NumPy arrays. And add a return statement here. To populate these two lists, we're going to iterate in num data divided by batch size. What this is doing is determining the number of elements that will be in the batched inputs and batched expected lists. Let's say, for example, batch size is 32 and the number of data points we have is 64. Then we're going to have just two batches of size 32, which is 64 divided by 32. And that's what this is ensuring. If the number of data points was 65, even then we would only be able to create two batches of size 32, which is why we're using the floor division operator. So in each batch, we're going to define a batch imp, comma batch x, and these are also going to be two lists. Then let's just change this to I, and then for j in range batch size, this will allow us to collect batch size number of input data points in the batch input and batch expected lists. We're going to append batch imp.append input data at the index indices batch size times I plus j. What this is doing is it's calculating the current index that we want to add, which would be batch size times I plus j. Then we're going to get that index from the indices list, and we're going to get the input data point corresponding to that index using this syntax. Similarly, we're going to append to the batch exp list the same value from expected. After we have populated batch inp and batch exp with batch size data points, we're going to append batch inp and batch exp to the batched inputs and batched expected lists. So batched inputs dot append np dot array batch inp and batched expected batch exp. This is how we're going to batch our data points and then pass the batches into our model for training. Finally, after our training is done, we want to implement a predict method, which, given a set of inputs, will return the model predictions. This would be our training dataset or our inference dataset. So after our model is trained and we want to test it out on other data that it's not been trained on, we will call the predict function. Here, we're going to create a list called predictions, which will store the predictions of the model for each input. Then we will iterate through each input in the inputs argument provided, and we will append to predictions the result of passing that input into the model. And that would look as follows. Self inp. We will then return the predictions of the model as follows. One final thing that we have to keep in mind is that since we're using batching in our neural network, we need to ensure that this inp that we pass in the model in the predict method has a shape equal to 1, num features. But if we use this syntax, then this 1 will be missing and we're going to get a cannot matrix multiply error. To resolve that, we're going to use this function called expand dims. And the expand dims takes a NumPy array, the dimension in which to expand the array. Here, the axis would be 0 because it's the first dimension that we want to increase. And that is it. That is the entire layer list class and layer class in this file, the activation functions, and the loss functions. Now, as promised, let's put all of this together and build a handwritten digits classifier in main.py. In order to save time, I've put the code together up here for us to follow through. First, we're going to import NumPy and matplotlib for calculations and graphing. Then we're going to import all the classes that we wrote in the activations, the loss, and the layer files. And then from sklearn, we're going to import the datasets. We're going to then load the mnist digits dataset using this syntax here and extract the images and labels. Then we're going to use the built-in train test split function to split the images and labels into training and testing data points. We're also going to reshape the training and testing images because each image is an 8 by 8 matrix, and our model will take only a one-dimensional matrix. So we're going to reshape this to be a 1 by 64 matrix. Next, we're going to convert each of the labels into arrays of probabilities. Since this is a classification task, we want to make sure that the expected values are arrays of probabilities. We're going to do that using this syntax here. We're iterating through all the expected labels in the training dataset. We're creating a list of size 10 with each value initialized to 0, and we're going to update the probability of the label to be 1. This is going to convert each label. Let's say the label is 2 into lists as follows. And the value that is 1, its index will indicate the label. We're going to convert these lists of probabilities into a NumPy array and reshape it to match the final layer of our neural network. Before we go through these two functions here, let's just go through how we write our neural network. We're first going to scale the input data to avoid exploding gradients. That is, if the values in our testing and training dataset are greater than 1, then there is a chance that during the matrix multiplication, the gradients get stuck in a vicious cycle where they exponentially grow and result in an unusable model. We'll also define these hyperparameters here, the learning rate and the batch size, and we'll write our classifier as follows. So it will be a layer list object with two layers. The first layer will have 64 inputs and 28 outputs, and the second layer will have 28 inputs and 10 outputs. These 10 outputs represent the 10 labels for the 10 digits. Additionally, since it is a classification task, we're going to use the Softmax activation function in the last layer. To train the model, we're going to use the fit method. We're going to pass in the reshaped training dataset, the reshaped expected values, the number of iterations, or the number of times we want the input data to be seen by the model, the alpha value, the batch size, and the loss function. We're going to use categorical cross entropy loss here because there are more than two labels that we can classify into. After the training, we're going to evaluate the model using the classifier.predict method. We're going to pass in the testing dataset, and we're going to convert the results of the model into a list of labels using this convert function. The convert function takes in the classifier predictions, which would be a list of probabilities. Then it will find the index of the largest probability as follows, and it will append that index into predictions because that's the label that the model is predicting. Finally, we're going to pass all of that into this display images function, which is just a nice helper function to display the images and the model predictions for us to visually evaluate. Let's try running this and confirming that the library works as we expect. Oh, so it should be activation func and not activation. That's the keyword argument. Let's try running it again. Okay, I found the reason why it's happening. It's because here we didn't pass in the index here. So we were passing in the entire batched input matrix and not each batch in the batched input matrix. Let's try again. Oh, oops, that is again another tiny mistake. We can't multiply the current inputs with the ret. We have to, in fact, transpose it. That is, we need to switch the rows and columns of the matrix to ensure that the shapes match. I would recommend you to draw out the current inputs and the ret matrices and see why the shapes don't match if we don't take the transpose of the current inputs. And similarly here, we need to take the transpose of this weight matrix. And there we go. That's our model's performance on the testing dataset. As you can see here, the first value is the model prediction and the second value is the expected label for each of these digits. And we can see that the model is done pretty well overall. There are a couple of issues, like here it's predicting this 1 is a 9. Here as well it's predicting this 1 to be a 9, as well as here. And here it's mistaking this 1 to be a 3. Oh, and here it's mistaking this 8 to be a 5. But overall, if we go through this, it looks like most of the digits have been classified correctly. We could, of course, tune some of these hyperparameters, add a few more layers and different activation functions to try and improve the model, but that's up to you. Do feel free to play around, add more layers, try different activation functions, a few activation functions that you write by yourself, and see if you can get your model to perform better. You could also use this model on other datasets that are available. You could also try this in some regression tasks where you have a bunch of input data points with a certain relationship that you try to predict using a neural network. The possibilities are just endless. With that, we have finished the implementation of our bare bones neural networking library in Python using only the NumPy library. Feel free to comment if any part of the code is unclear to you or the math is unclear, and I will do my best to help you understand. See you all in the next series.